Recording start. You can see the bottom, huh?
Yes, Mr. Mazen.
Okay. Okay, let's see. Okay, so I would like to welcome everybody to our second webinar in 2025, and I would like to thank Mr. Ibrahim Milad to dedicate some of his time for this volunteering activity with the SPWLA Iraqi branch. I will make like 1 minute just presentation for our activities for SPWLA. And before that, I will leave the mic for Dr. Mohammed. Dr. Mohammed.
Yes, Mr. Mazen. Hello, everyone. Today is the 10th of February 2025. On behalf of the SPWLA Iraq chapter, we are thrilled to welcome you again and have you join us today. My name is Muhammad Jawad Zainul Abedin, and I am the Vice President of Technology at the SPWLA Iraq chapter, as well as a senior faculty member in the Department of Petroleum Engineering at the College of Engineering at the University of Kirkuk. This is the second webinar into 2025, predicating geological facies in complex reservoirs, harnessing machine learning, will be presented by our speaker, Mr. Ibrahim Milad. Welcome again, Mr. Ibrahim Milad. Dear attendees, please note that during the presentation, we will share a link in the chat box to join the SPWLA Iraq chapter on LinkedIn. Thank you. Mr. Mazen, the floor is yours.
Thank you, Doctor. You can see my screen that I just shared.
Yes, sure.
Okay, so welcome again for our monthly meeting with SPWLA Iraq, and I'd like to thank again Mr. Ibrahim Milad. This year will be our focus will be on artificial intelligence application in geoscience and petrophysics domain. This lecture will be about predicting geological facies in complex reservoirs, harnessing machine learning techniques, by Mr. Ibrahim Milad from BP company. We are planned to do 10 to 8 webinars. Okay, at least we are confirmed 7 of our webinar for this year. Next webinar will be with the Spotify company with Mr. Athir Attar, where he will utilize Spotify software for petrophysical data analytics. Other webinars will follow, okay, with Microsoft, Baker Hughes, OpenAI, GeoActive, and other companies. We'll keep you updated for sure. Please follow our LinkedIn page. As usual with every year, I'd like to thank for all our attendees that attend more than our 6 webinar. They will get a special certificate of super learner. Okay, last year 3 personnel had been managed to get this certificate: Mr. Abbas Radi, Mr. Aus, and Mr. Delvin. And we are appreciated if you like to join Iraq chapter. Thank you all, and welcome to our webinar. The floor is yours, Mr. Ibrahim.
Thank you very much. Let me try to share the screen. Is it okay? Do you see my screen?
Yeah, crystal clear.
Okay, clear. Thanks for SPWLA Iraq for the invitation to speak to you today. Thank you very much. Today I'm going to talk about geological facies prediction in complex carbonate reservoir utilizing machine learning. This is one of the projects I was working on recently. But before that, I wanted to give you an overview about the subject and what's the main objective of doing this exercise. Automating automatic facies prediction for complex reservoir is an important step in characterizing reservoir heterogeneity and modeling and improve the model itself. That technique that we use was generated and tested in more than 1,000 wells. So we have huge data set to be used and utilized to create a prototype model that can be learned with experience. This work represents a workflow that utilize machine learning algorithm that accept a set of well standard logs as an input and generate a distinct fascist type as an output. The approach itself is focusing on distinguishing between different fascist type from its reservoir properties and log responses. The algorithm itself can be utilized to other random wells in the dataset across the field, hence bringing automation to the workflow, validating the automatically interpreted logs, offer substantial time saving. As I mentioned, we apply that on 1,000 well. If we wanted to do that manually, that will take a significant time. The main goal actually was to improve the geological model, update the field fault model based on the geological model to understand the sweep behavior and also select new location that represent specific facies to be drilled for the new targets, which at the end of the day will leading to more optimal management for reservoir performance. When we start this exercise, we set a success criteria for us as a team to see if we can utilize machine learning to help us to predict geological facies. And I listed the main success criteria that you should think when you try to apply the same approach in your field or any study area. You need to appreciate these 6 factors. You might be able to add to it if you like, but this is the 6 criteria we put as a team to label if we are successful to predict facies or not. The first one, the original data set, should contain wells represent the lateral heterogeneity. This is hypothetical map shows the structure, for example. So the data has to be covering the entire field. In our case, we have more than 1,000 wells. So we have select wells that represent the different heterogeneity of the field, well from north, from south, on the crest of the structure, and also on the flank. So we can represent that lateral change in the facies. So the learning model will be well learned that so can predict geological facies in good way. Data quality is also very important. So for the training data set, the wells we select as a training data set, the logs data has to be good quality, not affected by well power condition or any other thing, because this is the DNA of the prototype model. So the data itself has to be good to improve the predictivity of the model. The data subset should contain sufficient data for robust splitting between training and blind data set, which means that the well, yes, it has to have good data set, but complete set of data. For example, if the well missing neutron or density log, we should avoid that from the training data set, even though the data quality, the rest of the data quality is good. We need complete set of data. And the data subset should be supported by core data. So in the training data set and the validation data set, we have to have core data because core is providing physical examination of the facies. So it will be the reference for us to see if the model is predicting correctly or not. The accuracy of the prediction also should be within the required tolerance. So automated result can be applied with confidence. So we need to understand what's the success criteria for us. What's the accuracy rate we're looking for? Is it 50% is okay, or 60% is okay, or maybe 70% is okay? So we need to be to set a success criteria. And also we shouldn't be very optimistic, especially when we apply any machine learning algorithm on complex data set. We should be reasonable when we set the success criteria for us. And most importantly, the gain of time due to automation must overweight the burden associated with the machine learning interpretation. So if you have a study area of 6 wells, I will advise you not to use machine learning. You can do the interpretation manually, and yeah, end of story. But if you have large data set like 80 wells or more, or thousands of wells like our case, then the machine learning will be reasonable to spend time on. I would like to take you now through the methodology. I try to simplify it, use simple term for people who are not familiar with that approach of machine learning. So the methodology can be divided to 3 stage: learning stage, prediction approach, and then the validation stage. In the learning, we selected 19 key wells in the area. We picked the fascias manually on those 19 wells as foundation for the prototype model. And then we create a composite learning well that contains all the properties and features of these fascias from all 19 wells. Sorry. The inputs for the composite learning well, so we add the manual fascias, we add gamma ray, neutron density, deep resistivity, porosity, permeability. And then later on, we add something we call it large pore index. The large pore index is a curve we created to estimate the large pore proportion from the porosity. And that curve comes from the NMR data, in carbonate reservoir, this LPI curve is very important because it represents the pore size distribution. As we know in carbonate, sometimes the porosity has different size distribution, and that might be representing different fascias. In other simple or clastic reservoir, you might not need to add large pore index curve like this one. So our inputs are 7 inputs. And then we use 2 methodology. We use the MLP, multi-layer receptron. The outcome from this model was acceptable. However, MLP is a black box, so we cannot get inside the algorithm and try to improve the prediction. And this is for us is downside because, as I mentioned, the reservoir is complex, and sometimes we need to maintain or improve the algorithm itself to fix specific, prediction for specific fascias. We also tried the decision tree. The outcome was superior actually, and the advantage of decision tree that we can actually improve the prediction by make alteration to the script itself. One of the main goal was to use a platform that can be used by all geologists and petrophysicists. In our case, we use TechLog. TechLog has the advantage of having some machine learning algorithm embedded in the TechLog as a commercial platform. So the objective was that if we wanted to do this exercise, it has to be easy to use by all geologists and petrophysicists. So we try to avoid using any other platform that cannot be provide easy accessibility for all users, and or it's very complex that needs scarce skills in data science to be used. So in our case, we use TechLog. For the validation, we use 5 wells as a validation data set. We created composite validation well for them, and we did the validation process, and I will talk about that in more detail later on. The validation or the model accuracy. So, and this is very important step to see if the prediction is successful or not. We use the anchor tool, which is a tool included in the TechLog. The prediction success on the learning data set was 97%, which is expected because this is the learning data set. In the test well was 60.4%. It is acceptable for us because our success criteria was 60% success rate. However, when we look to the more detail to this 60%, we will see that it is actually more than 60. It's around 74% if we focus on the key fascies that we are interested to increase the prediction success rate of them. This is the cumulative prediction success. In the learning data set, we have 7 fascies. We have, I colored the fascies with specific color, and I will add this box for you as a guidance during my presentation so you can relate the color to the name of the fascies. We have lagoon, we have back shoal, we have shoal, we have channel fascies in yellow, we have proximal mid-ramp, we have distal mid-ramp, and we have cemented fascies. We call it cemented fascies because it's tight fascies. The percentage of the fascies is very important to understand the percentage of the fascies in the learning data set. And also in the validations dataset. So if we look quickly, the prediction success rate for all fascies in the training dataset is very good, as I mentioned. In the blind test, it's 60%. But if we look to the back shoal fascies, which is the best quality fascies for us, these are the fascies that dominate production, and the success rate of these two fascies is very important for us. If you look to the prediction success of it, it's altogether it's around 75%. But the misprediction of the shoal fascies either will be back shoal or channel, and also these are very similar fascies. So if the prediction success was wrong, it is not too wrong. It is within the tolerance. Meaning that we haven't predicted good quality fascies by poor quality fascies. The good quality fascies always successfully predicted. And I will talk more about why we're having this complicity in carbonate reservoir. One of the main challenge we had during the exercise is the type of data. When we went through the verification and acceptance criteria for this work to be verified and approved, the data science people said that the anchor tool is not the proper tool to be used to verify this work, and we prefer to use the F1 score because the data is unbalanced data. And that's true, to be honest. The data is unbalanced data. If you look at the percentage of the data, we have 35% back shoal, we have 24 shoal fascies, we have 22% channel, 16%, 6% and 4% from other fascies. So the data is not balanced. And that's, yes, that's correct. In this case, we cannot use the anchor tool. And to do that, to qualify the data, either you use F1 score or you need to remove or move the data to be balanced data. And this is what we have done. If we split the data set to good quality fascies, which is shoal, back shoal, and channel, that represents 62%. Poor quality fascies represent 38%. So the data, now, if we looked at the data from that perspective, then we can use the anchor tool to qualify the prediction success. Because at the end of the day, if we mispredict the back shoal with shoal, it's not significantly different. Yes, the deposition setting is not pretty much the same, but both of them are adjacent to each other in the geological model, and the reservoir property are overlapped. And I will show you that in some cross plots. So the data overlapping, which is the challenge number 2. If we plot the porosity permeability for all fascies, and we color the fascies as we agreed in the previous slide that we have specific color for each fascies, you can see that some fascies actually are overlapping. So to predict the fascies from the reservoir property, the model might sometimes mislead the prediction because the reservoir property are similar. But when we split the fascies to for example, the first row here, which is channel shoal, back shoal, and all the good quality fascies all together, you can see that there is some overlapping, but we still can distinguish between the back shoal, and channel somehow. But if the reservoir properties actually sharing both of the shoal and back shoal, the model might struggling in terms of defining the fascias itself, but reservoir probability again will be the same. That's apply for the for poor quality fascias. I plot the porosity permeability for each poor fascias separately, and then I add them together. The only fascias which has distinct trend is the cemented fascias, and which was the best poor quality fascias can be easily predicted in the model. Distal midramp, proximal midramp, and lagoon. The model sometimes struggle to differentiate between them. Now let me show you some real example. Okay, I talk you through the methodology, the challenge that we're facing, and now I will share with you some results, some real results. So we have two examples. This is the first example is learning Hurdwell. In the column, I have labeled each track, so you can see open hole data, porosity, permeability. That's his LBI, which is mere large pore index. And again, this is the proportion of the large pores within the porosity. This is the manual fascias, the first column. This is machine learning smoothed fascias. This is the machine learning detailed fascias. This is the probability success of the machine learning. So if you focus on these two columns, the manual fascias and the machine learning fascias, you can see it's very identical, which is expected for the learning data set. And for people who are working in this business, they might say, okay, because we are using decision tree, might be indication of overfitting. But I will show you in the next example in the validation data set that this is not the case actually. Sorry. So in the validation data set example, this one has core data. This is the manual fascias. Okay.
Just a quick question. Sorry about that.
Question at the end of the presentation.
Yes, please.
Okay.
Can you mute? Okay, please.
So we have manual fascias, okay, and we have the machine learning smoothed fascias here. You can see some discrepancy between the manual fascias and the machine learning fascias. When we go back to the core data and to just try to verify why the model is mispredicting this, we found out that the model actually predicting successively when we compare the machine learning to the core data directly. This is the manual fascias. We did it sort and rush. We were rushed to do that. But the model says, okay, you define this as a lagoon, but actually the top of this fascias is lagoon, the rest is back shoal. And when we look to the detail of the core and the averages of porosity and permeability, that's make more sense actually. So we decided, yes, the model is not overfitting. Instead of that, the model is predicting much better than the manual prediction. Also for these two fascias, our manual picking was all of this section is shoal, but the model saying no, we have back shoal at the top and back shoal at the bottom. And if you look at the porosity change, permeability change, and large pore index, that makes sense. So this fascies is not shoal, it should be back shoal, which was really a good news for us that the model can be improved and learning from experience. And I mean by experience, by introducing the model to more data. Validating the model with dynamic data, which was very important step for us to see if what we predicting when we perforate that predicted fascias, do we have the same rate or the high rate? For example, if we targeting the shoal fascias, which has good porosity permeability, first, is the fascias has been predicted successfully? Second, does the fascias producing the rate that expected? For example, in this well, we have, again, I labeled each track. This is open hole, porosity, permeability, BLT, saturation data. We have sigma, carbon, oxygen, and this is the predicted fascias from machine learning. And this is the detailed fascias. I mean by detailed fascias, so it's more detailed scale. In this track, we do some smoothing to be able to, map it later on to translate that to the map. And you can see, for example, for the shoal here and here, we have good porosity, good permeability. We perforated both zone, and it's dominating the production. You might ask why we are not producing as much from this perforation. This is related to the pressure issue. So the pressure in this zone is less than this zone. So it doesn't is not able to produce the same rate as the bottom one. Another example, we've seen the model is predicting short channel fascies. This channel fascies, the percentage of this fascies in the field is not too much. And when we saw the model is able to predict it, that was good news also for us, because this fascies is very productive fascies. And we picked the fascies very correctly, producing dominating production. Also, the shoal good quality fascies was predicted successfully, and it has perforated. And again, it doesn't produce because the pressure issues in the field that we know already before. The business impact, what's the big picture of applying machine learning and generating, updating geological model across the field is to understand, again, to update the full field model and also to understand the sweep efficiency. And this is one of the example, one of the problem we've seen in some data that we have water over oil, like this one here. We see some oil in the bottom and water above. And we wasn't able to reflect that in the model. But when we did the prediction, we understood what's happening. If you see the permeability, this is the same one. This is just a drawing model. The sweep in the good quality fascies, which is the shoal, is much better than the back shoal. And when the aquifer starts supporting from the flank, the good quality fascies, the shoal will be swept, but the back shoal fascies will be not swept. So the sweep efficiency in the back shoal fascies is less than the shoal. Understanding that across the field is very important for modeling when we create full field model or small sector models, to understand where we should put the injector, how the aquifer is working, and which area will be swept, and which area in the producer we have to perforate, and which interval we need to avoid because it will be wet. The conclusion, a prototype. This is a prototype model and algorithm based on decision tree classification for more than 1,000 well. The geographic representation of the data, as I mentioned, is very important. Understanding the model performance is also important. In the anchor table, the score was 98% for the training data set, 60% of the blind test, as I said, but this is actually very good performance given to the reservoir heterogeneity. The overall prediction success of good reservoir quality fascies, back shoal, and channel was representing 62 of the total interval thickness of the blind test data. This is even better with 71 to 74 correctly predicted for these fascies. Time saving, it saved us more than 5 or 6 months of manual flagging of the fascies. So it saved us a lot of time and money. The automated fascies prediction workflow has just demonstrated an ability to predict different fascies that was manually predicted wrongly. So the model can pick any fascies has been predicted manually by geologists or petrophysicists that does not represent the right reservoir property or petrophysical property, and correct that in the model. The improvement in geological model prediction has been reflected in better geological model and dynamic simulation. It has improved the understanding of the sweep behavior and planning for new wells, leading to more optimal management of the reservoir performance. Thank you. And if you have any questions, please go ahead. You mute, Mazen.
Good evening.
Oh, maybe like this. Hello?
Yes. Okay. Yes,
Oh,
we hear you now.
yeah. Okay. So thank you so much for this informative and fruitful like presentation. Okay, I guess you compress a lot of efforts and work. Okay, in these slides. Okay, I have few questions from my side, but I believe somebody have been raised its hand. Okay, Arsene want to ask something?
Yeah, thank you first of all for sharing this idea and data you have. Please switch on the slide number 9. If you can. Yeah. Basically, I work as a geologist and geomodeler, and actually not familiar with Iraq geology, but for my understanding, in the bar where we have final facies, it's the last bar, yes, of the web.
Yes, this one. Yeah.
I see the thickness of final facies is really small, yes. And uh, what do you think? How we're gonna model them? I mean, in 3G, because thickness is really thin. I think
Yeah.
it's about less than 1 meter. Yes, some of facies, and some are not.
Yeah,
What do you think?
I can answer this. I can tell you. So the last one is the machine learning fascias, and it's in the final scale. Okay, this one here is the smoothed fascias, and we did that smoothing to remove that thin layer because it will be hard to be modeled, as you mentioned. Okay, so the modeler has asked me. This is this one here, the last one. This is the first product from the machine learning, because the prediction is based on the log response. And if you see the log response, there are a lot of heterogeneity in carbonate reservoir. The vertical heterogeneity, I'm sure you have seen some core data for carbonate. The vertical heterogeneity is very small scale, actually. So any change in the reservoir properties was reflected in the machine learning. And this is what we see in the core, right? The vertical scale is very tiny if we have very high vertical heterogeneity. But that we cannot be modeled, okay, that fine scale. So that's why we did some smoothing. We use 20-meter window, and then the modeler asked me to keep it 25-meter window. But the one I'm using now is 20 meter, because I think 25 will eat a lot of details. You know, the idea is the field fault model, there is mismatch between the predicted and the actual. There's no history match, and this is one of the problem, you know, because we propagating, as you know, reservoir property by fascias in the model, and if the fascias is not representing the vertical heterogeneity, then we might not representing the geological model actually itself. But again, you are right. This is very thin. It's hard to be modeled, and that's why we did the smoothed one, which has more thickness to it to be modeled.
Yeah, thank you. And the other question associated with fishes again, as I see, fishes code number 6 is cement, and
Cemented
as
fascias,
I
yeah.
understand, yes, it's not actually fishes. It's about property, yeah, because I'm not sure
Yes,
that
yeah,
cement
yeah.
is.
I agree. Yeah, you are right. There is no fascias you can name it cemented fascias, but it is a localized name for us, to be honest, because it's geologically it's very bioturbated and very solidified. Okay, so we name it just a name for us because it's not reservoir. It's very ugly in shape with the core, and it's annoying, you know. So we call it cemented fascias between us and the team. But yes, there is no
Thank
thing
you.
in the textbook says cemented fascias. You are correct. Just a
And
name, you know.
uh,
Yeah.
And the last question, as I understood, geologists and petrophysicists work together in TechLog, yes, to identify the main wells, and then petrophysicists did some machine learning work in TechLog, some plugin, as I guess. What plugin is it, or
Yeah, we use TechLog plugin of 2020. TechLog. There are two machine learning, if you like, prototype models embedded in TechLog, MLP and decision tree, both of them. And again, as I mentioned, we didn't use any platform out of TechLog or Petrol, because the idea is that this model has to be used by everyone. If we use very complicated model, which might end up with the same result, then it will be hard for any geologist or petrophysicist to understand the algorithm and try to fix it if needed. However, data science people in BB ask us to give them the data to try neural net technique, which is out of the TechLog environment completely, and they end up with very similar results, because they said we cannot approve the model and the verification of the model unless we try a blind test for the data by using different platform. And that's the main goal, ease of use. If we make it very complicated, it will not be popular and nobody can use it.
Okay, thank you. Now, as a geologist, I know how to squeeze some more data from my petrophysicist. Thank you.
Thank you, Arsene. Mustafa, you have a question? Mustafa?
Yeah, yes, please. Good evening, and thank you very much for your presentation. I think my question, I've got two questions. You had mentioned use of NMR data in terms of the pore index. Is that part of your inputs parameter when you are constructing the model?
Yes, it is, yeah.
Okay. So that means you have lots of NMR data for you to have done that, because you had mentioned that if one particular curve is missing, you cannot apply them in other wells.
Yes, that's correct. So we have around 180 wells with NMR, okay? But as I mentioned, we have more than 1,000 wells. So there is another paper, there is another piece of work we've done. So we create a large bore index in the 180 wells that has NMR in it. For the rest of the wells, there is another piece of work we might present in a future webinar, talking how we can predict the large bore index in the wells that has no NMR in it, okay? So we use that 180 well across the field to start predicting the large bore proportion in the wells that has no NMR. So we have large bore index in all wells. Some of them from NMR, some of them from machine learning.
Okay, sounds good. So thank you very much. The plot that you showed, the very plot the other gentleman talked about, number 9. Yeah. Have you got core in this particular example?
This one or the other one?
Yeah.
This one, okay.
Well, yeah. Do you have core data in this?
Yes. This is learning core well, and this is test core well. Yeah. The core data is essential in this stage to verify the machine learning, so if we don't have core data, it will be not verified, how you know that the model is predicting correctly.
Yeah, that's where my question is going. So if you put the core data on the flashes, how do they fit?
Yeah, with the detailed fascias, this one, it fits very well. For example, you see the lagoon, okay? This is the bank. This is lagoon fascias, okay? You see the spikiness in the porosity and permeability. This is because the lagoon fascias makeup itself, if you are a geologist, you will understand what I'm saying. The lagoon depositional setting is thin layer of good and poor reservoir quality. That's the depositional setting of lagoon due to the fluctuation of the sea level rise. Okay, sometimes it's good, poor, good, poor, good, poor, and this is what we've seen in the core data, and it's the same being predicted in the fine scale machine learning. Okay, however, as I mentioned,
Thank you very much.
we tend to do some smoothing to be able to model it, to feed it and put it in the model. So there is a good match between the core data.
Okay, thank you very much.
You're welcome.
Thank you. Thank you.
Yeah, I do
Mr.
appreciate that you produce or did this work on Techlog, but I also would like to emphasize that the IP to produces a very good results. I cannot compare it to Techlog in any way, but I feel the IP also give a fantastic result on this. So,
Yeah.
thank you.
Yeah. We don't have IP licenses, unfortunately, but yeah, IP is a good software as well.
Thank you. Thank you, Mustafa. Mr. Salim, you want to ask something?
Yes, sir.
Yes.
Yes, sir. Good afternoon or good morning. Mr. Ibrahim, it seems like a very interesting and good presentation you just made. I'm sorry I came here late because I did not, that shift in time I was late. But I have
That's
just
all right.
one question, one question about slide number 9. Okay, the facies description or fascias description. Okay, when you say lagoon or shoal or channel,
Yeah.
this is rather than not fascias or facies, it is environment, because when you say channel, the channel can have sand and can have shale on the bank of the channel. So I want to clear this. I'm not doing any
Yeah. Are you a
any
geologist?
critique. I am old geologist, old
Yeah,
geologist.
I understand. I offended you, sir. Sorry about that.
No, you didn't offend me. I'm just
But yes,
I
you
don't
are
know.
right. To be honest, yes. Yeah, channel, it's the positional body, I would say channel. Okay.
Right. The environment. Was it
Environment.
channel? Was it lagoon?
Lagoon, it's
Shallow?
environment.
Yes.
Yeah.
Yeah.
For us, the
I-
terminology, we, as I said, so for this fascist scheme, the simplicity
Yes.
was very important. So, and we have
Yes.
multi-discipline team of reservoir engineer, petroleum engineer, petrophysicist like me, and
Yes.
chief geologist and geologist. And when the
Yes.
geologists start talking about complicated names, the other disciplines struggle to understand. In oil industry, as you know, simplicity is the key thing. So we want to simplify the
Yeah.
terminology.
I
I will ask the
understand. Yes.
geology to if he allowed to share with you the detailed fascias analysis with the right terminology and all the sedimentary structure and all fantastic thing. I'm happy to share it with you. But yes, you are right. Maybe this is misleading a little bit, but yeah.
Mr. Ibrahim,
Apologize about this.
it seems like great presentation. Let me, which panel is okay, that's the learning core wall. That's the test. Okay. And now I got it. Yeah, I got it. Was not
Okay.
clear in the previous slide. Shukran. Thank you so much. Was
More than
obvious, was a
welcome.
great presentation. I missed most of it. Thank you so much.
You are more than welcome anytime. Cheers.
Thank
Welcome,
you, sir.
Mr. Salim. It will be recorded and we'll send you email with the YouTube link if you like to watch it all.
I appreciate it. That would be great. Thank you.
Yes, thank you so much. Dear Ibrahim, there is a questions on the chat box if you like. There is one question from David. He said, can a fracture zone with various properties be predicted with high efficiency by applying AI?
I mean, it's a
zone.
good question. Define fracture from logs is a big challenge. Okay, so if the feature cannot be defined from log, I guess it will be hard to be predicted. However, we have another piece of work, another project, where we have been asked to predict fuzzy intervals, and that's under progress. We're trying to learn the model based on well-pore image, like FMI or whatever in vendor, okay, and UVI as well. So if we manage to successfully build a prototype model that can learn from this data automatically, and then yes, but as we speak right now, we haven't created a great success in that direction, okay. Also CT scan images, if we have like different walls in different location with CT scan image, that might be with core data, of course, that might be a good piece of information, can be embedded in any prototype model to predict. There is no limit for any to build any prototype model and make the machine doing the job, but the data set, how you make the model understand the data, is the big challenge, to be honest. But it's a good question, to be honest. It's a problem, and if we manage at some stage to do that, we're gonna to share it. But we're working on it.
Okay, that will be great. So if there is no more question, maybe I have very few quick question from my side. Yeah, so this like this have been published like as a paper or something. If somebody want to go extensive reading, or still not yet.
It will be published soon, actually.
Okay, that will be great.
Yeah, I can, but I can share. It's approved, to be published. So, but I haven't published it yet as a paper.
Okay.
So as soon as I publish it, I will share it with you, Mazen, and then you can share it in the SPWA Iraq website.
That will be really appreciated. I believe this module, like the base module, is not done by Python. It's done by plugin with Declog, as far as I understand. So with other software, I believe we need to use the software. There is no plugin can be shared. I mean, for Geolog, for example, like it's different.
Yeah.
It's different.
Yeah. It is combination, actually. So in some state, do you remember when I say the decision tree was not working in some fashions properly? So we supported that with some Python scripts. Techlog is working in Python language anyway. So I think we can use that script in any other platform. We can export the entire Python script structure, maybe with some maintenance. I would say it can be used in Bifrost on any other platform. But the point was to use the Techlog in purpose. But yeah, we can. I mean, we can.
Okay.
And also you can improve the productivity as well,
Okay, this will be great. So this question, and okay, people still try to come in. Okay, so just my last question. I saw there is a PLT, carbon oxygen, all these things. So these cased hole log have been utilized also to improve the model as well.
It wasn't part. Yeah, it wasn't part of the inputs to the model, but it was part of the verification, stage, just to verify. Does that shoal good quality fascies has been predicted correctly, and does it behave like shoal fascies that we know? So we integrate the PLT and saturation data just to understand if the model is working properly or not. For example, for sigma carbon oxygen, you can see the strong sweep coincide only with the short fascies and also the large production from that zone. So we use the PLT and or cased hole data for verification, but it wasn't part of the input in the model itself.
Okay, so it was like let's say practical verification, like to see if this one is really producing.
Absolutely.
Yeah. So this is not the same well. These are two different well. The one that you're presenting here.
Yes. Yes.
Yeah.
This
Okay. Yeah, I thought
different
there. Yeah, I thought like it's the same well, but there was some kind of programming. Okay, so it's two different well.
It's different
Okay.
wells.
Yes, I believe this will be the conclude of our presentation, and I'd like to thank you for your volunteering time.
Sorry, a quick one before Ibrahim disappeared. The final flagship, Mustafa again. I'm so sorry. It's just very interesting to me. It's a very good subject.
Can you make it quick, Mustafa, please?
Yeah, a quick one. The final flagship output, have you taken it further for permeability prediction?
The final fashes have been taken forward for permeability prediction.
Have you done that?
No, we haven't.
Okay. Okay, because now that you have PLT data, you know, it would be nice to see how it compares and see what that looks like really to predict permeability, particularly in areas that you don't have core.
Yeah, we have permeability model over the entire field, this curve. So we already have permeability as an input. So maybe I haven't got your question, how we take the fashes to predict permeability again?
Yes.
No, we haven't done that.
Okay, thank you.
You're welcome.
Thank you, Mustafa. Look like Mustafa so interesting in AI. Thank you, Mr. Ibrahim, for your time. I know you are a very busy guy. It was really appreciated. Dr. Mohammed, any last words before we conclude?
Sure, Mr. Mazen. Mr. Ibrahim Milad, thank you for your insightful presentation predicting geological facies in complex reservoirs harnessing machine learning. We look forward to having you again with the SPWLA Iraq chapter for more engaging webinars in the future. Dear attendees, thank you for your presence today. Wishing you all the best. We look forward to welcoming you to our upcoming events. Thank you, Mr. Mazen.
Thank you all. Any last word, Mr. Ibrahim?
Thank you.
Before we conclude.
Thank you for all of you to having time to join and listen to me. Thank you very much. I'm more than happy to do that again.
Thank you so much.
Thank you. That's really appreciated from your side. Thank you all. And we hope to see you in upcoming webinar with the SPWLA Iraq. As we mentioned, all this year will be focused on artificial intelligence. Okay. Thank you, Mr. Ibrahim. Thanks for all attendees. Thank you, Dr. Mohammed. I will conclude the meeting here.
Okay,
Goodbye.
bye-bye. Bye-bye.
Have a great day.